So we're reviewing for the final exam today, and we're just going to go through different types of problems that you have gone through in the semester and that you should know how to do. This is not going to be a full extensive review because we don't have enough time to review everything from this course in an hour and 50 minutes. So you should be able to solve, like I was just mentioning before the video was on, different types of equations. You should be able to identify what type of equation it is, how to solve it. You should also be able to identify if that type of equation may have extraneous solutions. So answers that actually are not solutions and that you needed to check your solutions. So in front of us, we have a radical equation and we want to solve for x. So if you're dealing with radical equations, the first thing that you want to do is you want to isolate the radical. If there's more than one radical in the equation, then you're just going to isolate one of them and you're going to have to repeat the process. So let's isolate our radical by adding x to both sides of the equation. And doing so, we get the square root of 2x minus 1 is equal to x minus 2. We can now square both sides of our equation to get rid of that radical. And that's going to give us back 2x minus 1, which is equal to, so we need to distribute this x minus 2 times x minus 2. So you have 2x minus 1 is equal to, so distributing and combining like terms, you would get x squared minus 4x plus 4 here. So after squaring both sides, our radical is gone. We don't have any other radicals in here. So now you have to identify that this is a quadratic equation. And normally when we go through and solve quadratic equations, we set the equation equal to 0. And so let's subtract 2x on both sides. And so doing so, we get x squared at negative 4x minus a 2x is minus 6x. And then adding 1 to both sides of the equation, we'll have 4 plus 1, which is 5, equals 0. So I notice this is factorable. If it wasn't factorable, I would probably go through and use the quadratic formula besides completing this, instead of completing the square. So there's two numbers that multiply to positive 5 and add to negative 6, which is negative 1 and negative 5. And so setting each factor equal to 0, we can see x minus 1 is 0 when x is 1. And x minus 5 is 0 when x is 5. So this is 1, and I'm going to see, and I'm checking to see that you're telling me that you checked it, and show me that these solutions work. So this is a case where we could get extraneous solutions. So go back to our original equation, and let's go first and plug in x equals 1. And so if we go in here, we plug in x equals 1, we have 2 times 1 is 2, minus 1 is 1, minus, plugging in 1, is this equal to negative 2? Well, 1 minus 1 is not equal to negative 2. That's equal to 0. And so right here, x equals 1 is not a solution. So we also want to check for x equals 5. So plugging in 5 for x, we have under the radical 2 times 5 is 10 minus 1. So we have the square root of 9 minus, plugging in 5 for x, is this equal to negative 2? 3 minus 5 is equal to negative 2. So this is a solution. So there's only one solution to this equation. So our next example is a rational equation. We have x all over x plus 1 plus 2 times x all over x plus 1 is equal to 8. So I noticed there's multiple ways to approach this problem. I was searching for a rational equation where we would want to clear our fractions. I'm going to start and do it that way, but I'm going to show you an easier way to do this if we used U-Substitution. So let's rewrite this. This is the same thing. This first term is the same thing as x squared all over x plus 1, quantity squared plus 2x all times x plus 1 equals 8. Because this is an equation, we can clear our fractions by multiplying by our least common denominator. And that is going to be x plus 1 quantity squared. Okay, so when we distribute this x plus 1 quantity squared to the first term, all we're left with is x squared plus, when we distribute it to the next term, one of the x plus 1's cancel, but we're left with one of them. So 2x times x plus 1 is equal to 8. All times this x plus 1 times x plus 1. So we have x squared plus, so distributing our 2x inside the parentheses, we have 2x squared plus 2x is equal to 8. All times, if I distribute this out, combine like terms, we get x squared plus 2x plus 1. Okay, on the left-hand side, we have some like terms, x squared plus 2x squared, which is 3x squared plus 2x is equal to, distributing the 8, we get 8x squared plus 16x plus 8. Quadratic equation. So let's get everything to one side of the equation. So let's subtract 3x squared on both sides. So 8x squared minus 3x squared is 5x squared. Let's subtract 2x on both sides. So we have 16x minus 2x is 14x plus 8 equals 0. So I noticed that this is factorable, and I can see that by the AC method. If I multiply my coefficient in front of x squared times my constant, 5 times 8 is 40. We're looking for two numbers that multiply to 40, but would add to 14. And I can see that that's 10 and 4. So we're going to use these two numbers, and we're going to rewrite 14x using those two numbers and then factor by grouping. So we have 5x squared plus 10x plus 4x plus 8 equals 0. So pulling out 5x, we get x plus 2. And pulling out a 4 for the last two terms, we're also left with x plus 2. So now we can pull out the factor of x plus 2 from both terms, and you're left with 5x plus 4 is equal to 0. So looking at when is x plus 2 equal to 0, that's when x is negative 2. And when is 5x plus 4 equal to 0? Well, if we subtract 4 or divide by 5, we get x equals negative 4/5. There was a value up here that x could not be, because this is a rational equation. We can't have values of x which sets the denominator equal to 0. So x couldn't be 1, and we're okay because our values aren't 1. Okay, let's say instead you decided, oh, I noticed this, I can use U-Substitution. Because notice how if we rewrite our original equation, just going to rewrite it a little bit. So we have this x all over x plus 1 quantity squared plus, think of it as the 2 can go out front of x all times x plus 1 equals 8. So let u be this x all over x plus 1. If that's the case, we're going to go in and plug in u wherever we see that. And so we have a u squared plus a 2u. I'm going to subtract 8 on both sides to set it equal to 0, minus 8 equals 0. We can factor this. This is u plus 4, u minus 2 equals 0. So looking at this, u plus 4 is 0 when u is negative 4. U minus 2 is 0 is when u is positive 2. We don't want u though, we want x. So when u is negative 4, so plug in negative 4, this is equal to x all over x plus 1. So we have negative 4x minus 4 equals x. So let's add 4 to both sides, 4x to both sides of the equation. So we have 5x equals negative 4. Divide by 5, we get x equals negative 4/5. Same idea with u equals 2. So 2 is equal to x, all times x plus 1. We could clear the fraction by multiplying both sides by x plus 1. So 2 times the x plus 1 is 2x plus 2 equals x. Subtract 2x on both sides, we get negative x equals 2, or x is equal to negative 2, which was the exact same thing we had gotten before, solving it by clearing the fractions. So either way works. Sometimes one is easier than the other. I don't know if you think that's easier or not. So in the next example, we're asked to find the difference quotient of f of x equals 2 over x. So recall that difference quotient is that f of x plus h minus f of x all over h. So you should know that this is not our function multiplied by x plus h, or our function multiplied by x. This is saying go in, wherever you see an x, you're replacing it with x plus h. So we have 2 all over, I see an x there, so I'm going to plug in x plus h, minus 2 over x. So it's subtracting off this function. And then all over h. Okay, so there's a lot of times in calculus that you're going to have to manipulate complex fractions and rewrite it as a non-complex fraction. So I might give you something like that to see that you guys can do that. So notice that we can clear our fractions. I mean, we can do that by multiplying by a fancy one. And that fancy one that we're going to multiply is that least common denominator of the fractions within the main fraction. So x all times x plus h is our least common denominator. So let's distribute that to each term in the numerator. And when we distribute it to the first fraction in the numerator, notice that the x plus h's they have in common, and those cancel. And so all you're left with is 2x minus, and now when we distribute this to 2 over x, the x's cancel, and we're left with 2 times the quantity x plus h. All over, I'm going to keep it in the factored form, so h times x plus h. So let's distribute our negative 2 to each term. So we have 2x minus 2x minus h all over, again, the h times x plus h. 2x minus 2x, those cancel. You're left with a negative h all over the h times x plus h. I noticed that our h's cancel here, so we're left with a negative 1 in the numerator all over x times x plus h. And so here's the difference quotient. of 2 over x. Okay, so we're going to do another difference quotient. This time, though, f of x is equal to the square root of x minus 1. So we want to look at f of x plus h minus f of x, and then all over h. Well, if we go in and we plug in x plus h wherever we see an x, we're going to get the square root of x plus h minus 1, and then minus f of x, so the square root of x minus 1 all over h. So let's manipulate this. We're going to multiply this by, again, a fancy 1. So let's get rid of those radicals in the denominator, in the numerator. And so we can treat this as multiplying to make it like a difference of squares. And so doing that, let's multiply by x plus h minus 1 plus the square root of x minus 1. So we're doing this, and we chose that. So again, that those are difference of squares. And we know that if we multiply a minus b times a plus b, that gives us back the square of the first term minus the square of the second term. So if I look at the square of the first term, that's just going to give me what's underneath the radical, which is x plus h minus 1 minus the square of the second term. So I need parentheses. I get x minus 1 all over h. So let's distribute our negative and then combine like terms. Oops, and I forgot that's not just all over h. I need to multiply my denominator by that square root of x plus h minus 1 plus the square root of x minus 1. So when I distribute that negative, I have a negative x plus an x. So my x's cancel. When I distribute the negative, so the negative 1, that's going to be a positive 1, but I have a minus 1 out here, so that cancels. So all we're left with is h in the numerator all over h. Need parentheses there. All times parentheses square root of x plus h minus 1 plus the square root of x minus 1. So h's cancel. And we're left with 1 all over the following. Okay, so as I was going through this problem, I was realizing you probably would have stopped without rationalizing that numerator. You probably wouldn't have known to go further. And the reason why my calculus students would know to go further is because they're looking at limits as h goes to 0. And when they plug in 0, wherever they see that h, they're going to get a 0, something that looks like this, 0 over 0, which doesn't tell us anything. It's an indeterminate form, and they would have to go over and manipulate it some more. And how they would manipulate it is going through and doing what we just did. So technically, how I could work around that is maybe not give you the difference quotient. I might start out and I could give you something that looks like this and say, rationalize your numerator. And so rationalizing the numerator means you're getting rid of the radical in the numerator, and you would know that you would have to multiply through by that fancy one, the conjugate of those radicals. Okay, so in front of us, we have the inequality, 3 minus the absolute value of x plus 1 is less than 1/2. Solving absolute value inequalities or equations, you want to isolate the absolute value if there's just one. And so in this case, let's subtract 1 on both sides. Not subtract 1, let's subtract 3 on both sides. And so we have negative absolute value of x plus 1 is less than common denominator here. So we have negative 6/2 plus 1/2 is negative 5/2. And you get rid of the negative in front of the radical. Oh, not the, I'm sorry, I'm a little out of it. In front of the absolute value. So if we multiply or divide by a negative with an inequality, that flips the sign. And so we're really dealing with x plus 1 and the absolute value is now greater than 5/2. Okay, so absolute value inequalities, you have to rewrite it when it's greater than. This is x plus 1 is greater than 5/2, or means union. What's inside the absolute value, x plus 1 is less than the negative of the other side, so negative 5/2. So we would solve each of these separately and then look at what the solution is for both of those and put them together. So if we subtract 1 on both sides, that's like subtracting negative 2/2 with a common denominator. We have x is greater than 5/2 minus 2/2 is 3/2. So it's strictly greater, so it's going to be looking like this. So it's halfway in here. So other inequality, again, we would subtract 1 on both sides. That is like a negative 2/2 minus a 5/2, which is negative 7/2. And so it's coming in from negative infinity to negative 7/2. So our solution in interval notation is negative infinity, comma, negative 7/2, parentheses, because we're not including negative 7/2, union, positive 3/2. There's a parentheses on that one, again, because we're not including to infinity. Okay, so just recall, if you had some absolute value of x is less than some constant c, then to drop the absolute value, this is where we sandwiched it in between. So negative c is less than x is less than c. And what we had just done was when it was greater, absolute value of x was greater than c, we have x is greater than c, or x is less than the negative of the other side, negative c. So those are the rules on the absolute value inequalities. Okay, so we have a system of nonlinear equations in front of us, x squared plus y squared plus 4x minus 2y plus 1 equals 0, and y squared minus 2y minus x minus 5 equals 0. And we want to graph the system of equations and find the points of intersection. So you should be able to identify, looking at each one of those equations, which conic section it is. And looking at that first equation, I can identify that's a circle because we have an x squared and a y squared in there, and the coefficients in front of the x squared and the y squared are the same. That second equation, y squared minus 2y minus x minus 5, I can identify that that is a parabola, and that's a parabola either facing the left or right direction, because it's the y squared and not the x that is squared. So let's first put those in that form where we can easily graph it. So here is where there was an example of a student that was able to tell me what the center and the radius was without even doing any or not showing any work. So to me, that's putting out a red flag that you're getting help other than just using your mind. So if that happens, then you're just going to get a 0 maybe for that whole exam. Another reason why I want to do an oral exam for this final exam. Okay, so we want to regroup our x terms and our y terms and get the constant on the other side. So let's do that for that first equation. So we have x squared plus 4x. We are going to add something in here to make this a perfect square. And then we have plus y squared minus 2y. We're going to add something in here to make this a perfect square, is equal to, and we want to get the constant on the other side. Okay, so looking at this first equation, we need to figure out what we need to add on this side to make this a perfect square. And so once your coefficient in front of the x squared or y squared is 1, then you're going to take your b value, in this case, which is 4. You're dividing it by 2, so we're having it, figuring out what can I add to itself to get 4. So that 4 divided by 2 is 2. I can add 2 to itself. 2 plus 2 is 4. So this constant, you need to square it, because the same number you're going to be multiplying together. So 2 times 2 is 4. So we're adding 4 to both sides of this equation. Same idea with the y terms. So half of -2 is -1. Squaring -1, though, is +1. So we're going to add 1 to both sides of this equation. Okay, so the first grouping, x squared plus 4x plus 4, this is x plus 2 quantity squared, plus that second grouping is a perfect square, and that's y minus 1 quantity squared is equal to 4. So the center in here is equal to -2, 1, and the radius is equal to 2, the square root of the other side. So we'll come back in and we'll graph this in a second. After I look at putting the other one in standard form. Okay, so because it's the y part that's squared, we're going to leave the y terms on one side and get everything else to the other side. And so doing so, we have y squared minus 2y. I'm going to leave some room in here because I'm going to add something to make this a perfect square. Is equal to, so let's add x to both sides of the equation. So this is equal to x. Add 5 to both sides of the equation, plus 5. And what we added to the one side, we have to add to the other side. So complete the square on y squared minus 2y. Well, dividing -2 by 2, we get -1. -1 squared is 1. So we're adding 1 to both sides of the equation. This right over here, this is y minus 1 quantity squared. Is equal to x plus 6. So I can see that the center, or not the center, the vertex of this parabola is at HK. h is -6, and k is -1. And I notice that my value out in front of the parentheses of this x plus 6 is positive, so I know that the parabola is going to be facing in this direction. Okay, so let's graph both of those. Okay, so looking at this, we have center -2, 1. And we know that the radius is 2. So from our center of the circle, we can go up 2, down 2, to the right 2, and to the left 2. Okay, so here's our circle. And then graphing our parabola, we have a point at -6, -1. And our parabola is going in this direction. So let's find some extra points. And so let's find our x and our y-intercepts, because this is something else I might ask you to do. So let's find, for the parabola, the y-intercepts. And so we're going to let x equal 0. And I'm going to go into the equation that we just found. So this is y minus 1 quantity squared is equal to, plugging in 0 for x, we get just 0 plus 6 is 6. So let's take the square root of both sides. And add 1 to both sides. So for the exact answer, we have 1 plus or minus root 6, but that doesn't really help me too much when I want to go graph this. So let's just estimate what those are. So 1 plus the square root of 6, that gives us back about 3.4. And 1 minus the square root of 6, that gives us back approximately -1.4. Okay, so it's pretty skinny parabola. Something's off. Seems to me that something's off because this needs to be symmetrical. Let me just look. Okay, so trying to figure out where this was on, and I knew something was off because I know that my graph is symmetrical across that horizontal line that goes through the vertex. And so those y-intercepts, it wasn't going to be symmetrical across that line. But notice up here, I need to take the opposite of the sign. And so that should have been, for my vertex, this should be a positive 1, -6 positive 1. Okay, so that's much better. So I'm not sure exactly where it's crossing, and I'll know more after we look at the solving for those points. So I don't know if it's just skimming of that circle and only touching it at one point on the top and the bottom, or is that giving us 4 separate solutions? Okay, so now we want to figure out the points of intersection. and you need to do this algebraically. Okay, so there's a couple ways that we can approach this. See if there's an easier way to do it. We could either use the elimination method here by subtracting off one equation from the other, and that way we will just have x terms maybe. Yeah, let's do that. I see that. So if we look at multiplying this whole equation by -1 and summing it to the equation above. So let me just write the equation above. We have x squared plus y squared plus 4x minus 2y plus 1 equals 0. Distributing the negative, and I'm going to put things so that they're underneath each other, like terms. So I get a negative y squared. I'm going to get a plus x. I'm going to get a plus 2y. And I'm going to get a plus 5 equals 0. So summing these two equations, we have x squared plus 5x plus 6 equals 0. So I notice there's two numbers that multiply to 6 and add to 5. So we have x plus 2 all times x plus 3 equals 0. So this is when x is -2 and when x is -3. So we want to go in here, we want to plug those in to figure out what y is. And so you're going back into one of your equations. All right, let's look at it using this one. If we use that one, then we can use the square root method in here. So let's use that one. So when x is -2, going back in here and plugging in -2 for x, we got y minus 1. Quantity squared is equal to -2 plus 6. So that's going to give us 4. You can use that square root method, taking the square root of both sides. So y minus 1 equals plus or minus the square root of 4, which is 2. So y is equal to, if I add 1 to both sides, so 1 plus 2 is 3. And 1 minus 2 is -1. So when x is -2, it's intersecting at 3. We'll say right here. And it's intersecting at -2, -1. So there's 2 points. And that was just for x equals -2. So let's look at when x is -3. Going back in here and plugging in -3 for x. So we have y minus 1 quantity squared is equal to -3 plus 6, which is 3. So take the square root of both sides, we get y minus 1 equals plus or minus the square root of 3. Adding 1 to both sides, we get 1 plus or minus root 3. So at -3, 1 plus root 3. And -3, 1 minus root 3. Which would be these 2 points right there. Okay, so again, a problem that shows me you know how to do a lot of different things. You know how to graph your conic sections, you know how to solve nonlinear systems of equations, and then you know how to find these intersections, points of intersections, which shows me in here that you know how to solve different types of equations. Okay, so solve the system with a method of your choice. So we have log base x of 2y equals 3 and log base x of 4y equals 2. So we could do substitution method, but in order to do substitution method, we need to solve for x or solve for y. Doesn't look like we can do the elimination method. And so first thing I would probably do is let's rewrite these as exponential equations and see if that helps us. So just using the definition of log, rewriting it as an exponential form, this is the same thing as saying x cubed is equal to 2y. Where the second equation, our base is x, raise it to the other side, x squared is equal to 4y. So we could go in and do substitution, or we can try to eliminate the y value by using the addition method. If we multiply this first equation by -2, that would clear out our y's when we summed it together. So this would give us -2x cubed equals -4y. This is x squared equals 4y. And so when we sum these two equations together, those are not like terms. We have -2x cubed plus x squared is equal to 0. So we could solve that equation by factoring. Both of those terms have an x squared in common. So let's pull out an x squared. And doing so, we get back -2x plus 1 equals 0. Setting each factor equal to 0 when x squared is equal to 0 is when x is 0. -2x plus 1 is equal to 0. Let's add 2x to both sides of the equation, divide by 2. So that would be x is equal to 1/2. So those are the x values of our points. So now we need to find the y value. And they also have to hold true for our equation. So I was just noticing, let's say I wanted to go back and plug it into our original log equation. This is saying that my base is 0. By definition, the log, our base has to be greater than 0. And so right here, this is impossible. Base has to be greater than 0 and not equal to 1. Okay, so right there, that gets rid of one of the solutions or values. And so let's look at plugging in 1/2. Okay, so if we plugged in 1/2 in there for x, we would have this log of 1/2 2y equals 3. Rewriting in an exponential form, I have 1/2 cubed is equal to 2y. So this is the same thing as 1/8 equals 2y. Let's multiply both sides by 1/2 to get y by itself. And so we have y here is equal to 1/16. And so point of intersection, we saw when x was 1/2, our y value is 1/16. Just make sure that, again, those values hold true for those logs. So log, if our base is greater than 0, not 1, has to of something, and that of something has to be positive. So if we plug in 1/16 into y for both of these equations, we're okay. We're taking a log of a positive number. And so we only have one solution, one place where those two graphs would intersect, and it would be at 1/2 and 1/16. Okay, so the next example, we're given a fraction and we're asked to write the partial fraction decomposition of the fraction 3x minus 5 all over x cubed minus 1. If the degree of the denominator was smaller than the degree of the numerator, we would use, or even the same, we can use the long division, but that's not the case here. You always want to see if this factors. And in the denominator, x cubed minus 1 does factor. It's a cubic. And so this is the same thing as x minus 1 all times x squared. I do it as opposite sign, so that's plus. It's going to be just x plus 1. That quadratic of the cubic is not reducible over the real numbers. If it was factorable, I would go further, but it's not. And so we need to rewrite this. So x minus 1 is a factor, it's linear, and it only appears once in here. So we're going to rewrite this as capital A all over x minus 1 plus x squared plus x plus 1 is irreducible over the real numbers. And so it's going to stay as a quadratic. Quadratics we write as bx plus c. So we write a linear piece on top all over the quadratic piece. X squared plus x plus 1. So once we broke that down, we clear our fractions by multiplying through by our least common denominator. And that's going to be x minus 1 all times x squared plus x plus 1. So when we distribute it on the left-hand side of the equation, the denominator goes away and you're just left with 3x minus 5. When we distribute it to the first term on the right-hand side, the x minus 1 cancels and we're left with a capital A times the quantity x squared plus x plus 1. Plus, when we distribute this to the bx plus c over that x squared plus x plus 1, the x squared plus x plus 1 cancels, and we're left with, and we need parentheses here. So bx plus c in parentheses, all times x minus 1. Okay, so let's expand the right-hand side. So bringing down the left-hand side, 3x minus 5 is equal to, let's distribute the a, we have ax squared plus ax plus a, plus distributing here, we have bx times x, that's bx squared, bx times -1, so minus bx. Distributing the c, we have plus cx minus c. So we're looking at the coefficients and matching them up on the left and the right. And so let's look at the square term, because I see square terms on the right, but there's no square term on the left. So we can think of this as 0x squared in here. And so I'm going to look at the coefficient of 0 on the left. That has to be the same thing as if I sum a plus b on the right. So now looking at terms with just an x in here, on the left-hand side, we have a 3 in front of the x. On the right-hand side, we have a minus a b plus a c. And then one more. So we have -5 here. So the constant on the left is -5. The constant on the right, though, is a minus c. So here's our system of equations. Okay, so here's another instance where I saw some what I believe cheating on the exam, where the students were able to come up with A, B, and C from this point right here, which there's no way without showing any work. So I want to go through matrices. So let's go through with solving this with matrices. Then I might say in here, use the partial fraction decomposition and use matrices to figure out what your coefficients are. And so let's do that. So our first row of our matrix is 1, 1. There's no C, so 0. But our vertical line, 0. Second equation, we have 1, -1, 1, and then we have a 3. And the third equation, we have 1, no B, so 0, -1, -5. So we always work column to column. I tend to like to get the leading coefficient in there first, which it is for that column. And so we're going to use that row to get rid of the numbers below that. And so let's look at negative row 1 plus our row 2. So row 1 is really staying the same. So 1, 1, 0, 0. It's just, we're just using it to change our row 2. So negative of 1 plus 1 gives us 0. Negative of 1 is -1, minus 1 is -2. Negative 1 times 0 is 0, plus 1 is 1. Anything times 0 is 0, plus 3 is 3. So let's get rid of the 1 in the third row, first column. And we could do that by looking at negative row 1 plus row 3. So -1 plus this 1 is 0. -1 plus 0 is -1. 0 times anything is 0. 0 minus 1 is -1. 0 times anything is 0. And then this would give us -5. So we finished with column 1. We want to move to column 2. We want to have a positive 1 in that second row, second column. I could multiply through that second row by -1/2, but then I'm dealing with fractions in there. And I would prefer if I can manipulate it without fractions to do so. So there's a couple ways we can do that. Remember, we can swap rows. So how about swap? I just lose my negative down there. I believe that was a -1 for some reason when I was erasing. Changed, but I can go check. Yeah, that's a -1. So let's swap negative row 3 with row 2. And that would give us a 1 where we want it. So our first row is staying the same, 1, 1, 0, 0. Our second row now, though, is 0, 1, 1, 5. Just multiplied -1 through the third row and moved it to the second. And our third row is what our second row was above. So 0 and -2, 1, 3. So we're using this 1 in here to get rid of the numbers above and below that 1. So let's look at negative row 2 plus row 1. So let's just go back in here and write row 2 because we're using it, but we're not changing it. So 0, 1, 1, 5. Okay, so 0 times -1 is 0, plus 1 is 1. -1 times 1 is -1, plus 1 is 0. -1 times 1 is -1, plus 0 is -1. -1 times 5 is -5, plus 0 is -5. Get rid of the -2 in row 3. And we can do that by looking at positive 2, row 2, plus row 3. 0 times anything is 0, plus 0 is 0. Positive 2 minus 2 is 0. Positive 2 plus 1 is 3. 2 times this 5, that is 10, and 10 plus 3 is 13. So looking at this, let's just go from here and read it off, because we've had it where there's zeros in this bottom half of the diagonal. We can read this off and do back substitution. And so we know our C, 3C, is equal to 13. So I'm going to say C is the same thing as 13/3. So let's write the second row down. So this is 1B plus C, but C we were just given, right, was 13/3. Let's just write that in there. Is equal to 5. So B is equal to, I'm going to subtract 13/3 on both sides. I'm going to need a common denominator. So I have a 15/3 minus a 13/3 is a positive 2/3. And now let's look at C. Let's look at finding C, and we're going to do that by using row 1. So we have, or actually we don't want C, we want A. So we have A plus 0B, so I don't have to write that, minus C, so minus 13/3 is equal to negative 5. So common denominator again. So adding 13/3 to both sides. So we have a negative 15/3 plus a 13/3. So that's a negative 2/3. So we're going to go back up and we're going to plug in what A, B, and C are into this piece. So we would get back, plugging in what our A, B, and C value are. This is equal to A, which we said was negative 2/3, all over x minus 1, plus B. B is 2/3 x, plus C, so plus 13/3, all over this x squared plus x plus 1. Personally, don't like that they're complex fractions. We can think of this if we wanted to as division, a fraction divided by a fraction, we're going to multiply by the reciprocal of what we're dividing by. So we could rewrite this as negative 2 all over 3 times x minus 1 plus, so notice we have a common denominator there. And so I guess I could flip it up. This right here is the same thing as saying 2x plus 13 all over 3 divided by this x squared plus x plus 1. That was just this piece though, not the whole thing. So I'm going to use that fact and then divide by x squared plus x plus 1. So invert multiply, we get 2x plus 13 in our numerator, all divided by 3 times this x squared plus x plus 1. So here is our partial fraction decomposition of what we started with, that 3x minus 5 all over x cubed minus 1. Okay, so that's all the time we have to go over problems. So I'm going to stop here. You guys have some reviews that you can look at online that I've posted. You also have a review tomorrow at the College Success Center. Let me just see what time that is. I believe it's 10 till noon, but let me make sure. College Success Center, 10 a.m. to 11:50 at the Marysville campus. There will be a review for college algebra. So for this class of my college algebra and the other college algebra class that I'm teaching.